Welcome back to AllAboutRx. Today, we're breaking down chemical bonding. Why do atoms actually bond in the first place? Well, it's all to lower their total energy and become stable. Let's dive into the different ways they hold themselves together.
Here's our roadmap for this explainer. We'll jump from an intro to bonding, straight into ionic and covalent bonds, check out sigma, pi, and coordinate structures, swim in the metallic sea, tackle hydrogen bonds, and wrap up with some absolute must-know memory aids. Section 1. Introduction to chemical bonding. Let's look at the fundamental drive of all atoms.
So chemical bonding is really just about atoms, molecules, or ions forming connections to produce a stable compound. When atoms get close to each other, their nuclei and electrons rearrange for one specific reason, to lower their total energy. If that resulting energy is lower than what the atoms had on their own, boom, a bond happens. That energy difference is what we call the bonding energy. It's all about chasing that stable, low-energy state.
Section 2. Ionic and covalent bonds. Let's examine the two heavy hitters of the bonding world to see how they achieve that coveted stability.
There's a pretty clear contrast between our two main players. For ionic bonds, think electron transfer. This is a permanent transfer of valence electrons, usually between metals and nonmetals, which creates the strong electrostatic attraction between a positively charged cation and a negatively charged anion. Now for covalent bonds, think electron sharing. Instead of just handing them over, these atoms share pairs of electrons so that both can fill their octets and get stable.
But, sharing isn't always equal. If identical atoms share their electrons perfectly equally, like in hydrogen gas or oxygen gas, it creates a nonpolar bond. But if that sharing is unequal, usually because one atom is more electronegative and hogs the electrons, like with hydrogen and fluorine, it becomes a polar covalent bond.
Section 3. Sigma, pi, and coordinate architectures. Let's drill deeper into the nuances of these shared covalent bonds.
Let's think about the architectural differences between these two. Sigma bonds are absolutely the strongest covalent bonds you'll see. Why? Because they're formed by a direct, head-on overlap of orbitals. It's a very solid connection. Pi bonds, on the other hand, are a bit weaker. They form from a sideways overlap of parallel lobes, almost like they're just grazing each other.
A super crucial point for your exams is this composition rule. A sigma bond is always present first. You literally cannot have a pi bond without a sigma bond already being there. A single bond is just one sigma bond, but step up to a double bond and you get one sigma plus one pi bond. A triple bond, that's one sigma paired up with two pi bonds.
We also have a very unique type of covalent connection called a coordinate or dative bond. Unlike your standard covalent bonds where each atom chips in one electron, here a single atom donates both of the shared electrons. The donor atom is the nucleophile and the acceptor is the electrophile. And when you're drawing this out, it's simply represented by an arrow pointing straight from the donor to the acceptor.
Section 4. The metallic electron sea. We've talked about individual molecules, but what happens when we scale up and look at the macrostructures of metals?
Imagine zooming way into a piece of pure sodium or zinc. In metallic bonds, the valence electrons aren't locked down to any single atom. Instead, they form this free-flowing, delocalized electron sea that just moves freely among closely packed, positively charged metal cations.
What's totally fascinating about this electron sea is how it dictates physical properties. Since these electrons are free-flowing and non-directional, they act like a buffer between the like-charged metal ions. This perfectly explains why metals don't just shatter when you hit them, why they're incredibly malleable, and exactly why they have such high electrical conductivity. The free electrons just ride the wave right along under an electrical field.
Section 5. The power of hydrogen bonds. Next up, a technically weaker intermolecular force that is absolutely crucial to biology.
So, why does hydrogen bonding even happen? Well, hydrogen is kind of unique. It has 0 inner shell electrons. When it bonds to a highly electronegative atom, its bonding pair of electrons gets pulled way away from the hydrogen itself. This leaves the hydrogen with a super high positive charge density, which basically exposes its bare nucleus to the lone electron pairs on nearby molecules.
In that exposed nucleus, it creates a massive impact. This seemingly weak interaction is actually powerful enough to hold together the mighty DNA double helix. It's what allows adenine to bond with thymine and guanine with cytosine. It dictates protein structures, and it even forces ice into a unique open hexagonal lattice,
which, by the way, is exactly why ice is less dense than liquid water and floats.
Keep in mind, hydrogen bonds can form in two distinct ways. They can be intermolecular, meaning they happen between separate molecules, like one water molecule sticking to another, which drives up boiling points. Or they can be intramolecular, forming within the exact same molecule. This internal bonding actually results in ring formation, also known as chelation. Interestingly, this lowers the boiling point compared to the intermolecular kind, simply because the molecules aren't sticking to each other as much.
Section 6. Essential memory aids. To wrap up this explainer, let's lock in some exam-focused memory aids so you can easily recall everything we've covered.
To synthesize our entire lesson, your master key for remembering relative bond strength is the mnemonic ICCMH. As a general rule, ionic is the strongest, followed by covalent, then coordinate, which is honestly roughly equal to metallic, and finally hydrogen bonds are the weakest of the bunch. Lock that acronym in, ICCMH.
Our next crucial rule is one you should absolutely never forget, the NOF rule. Hydrogen bonding doesn't just happen anytime hydrogen happens to be around. It only occurs when hydrogen is attached directly to nitrogen, oxygen, or fluorine, NOF. Remember, if it's not one of those three, it is not a true hydrogen bond.
Here is a rapid-fire review highlighting the main takeaways from today's explainer. Ionic is transfer, covalent is sharing. Coordinate means both electrons come from one atom. Metallic is at electron C, and hydrogen follows the NOF rule. You should definitely grab a screenshot of this for your study notes. It's a perfect cheat sheet for your organic chemistry foundation. So here is the big question. Could understanding these exact bonding principles be your first step to designing the next life-saving pharmacological drug? Since hydrogen bonds directly dictate drug-receptor interactions in pharmacology, mastering these fundamental principles really could be your first step toward a major medical breakthrough. Master these, and you've got the backbone of organic chemistry down. Check the link in the bio for more study notes. Like, subscribe, and stay tuned to AllAboutRx.